lecture on the respiratory system. At times, your respiratory system needs to be evaluated, and there's several parameters that can give information to the status of your respiratory system. These are the respiratory volumes and respiratory capacities. And I'd like to go over these volumes. These are various volumes of air, basically, that can be inspired or expired or retained in the lungs. These are used often for clinical settings to evaluate somebody with pulmonary problems or pneumonia, or lung problems, congestive heart failure, something like that. The first thing I want to talk about is tidal volume. Tidal volume, you're sitting there at rest, you're breathing in and out. The amount of air moving in and out of your lungs with each breath while you're resting is tidal volume. It's represented on this diagram here by the light blue color. You can see the lines go up and down, indicating inspiration and expiration. That's the tidal volume. The inspiratory reserve volume is the amount of air that could be inhaled forcibly after tidal volume inspiration. So you're sitting there breathing normally, your tidal volume, you're breathing in and breathing out, you're not stressing, just breathe in. After you breathe in, after you inspire normally with tidal volume, suppose I ask you to take in all the air you could take in. Then that would be inspiratory reserve volume. And that's represented here. It goes all the way from the upper limits of the tidal volume, and to inspire all this extra air can be inspired. There's an expiratory reserve volume as well, and that's the amount of air that can be exhaled after a normal tidal expiration. And let's say you're tidal volume breathing, and you expire, but yet you could expire more forcibly if you had to. So you're breathing out, and then if I ask you to breathe out all the air you can breathe out, that's going to give you the expiratory reserve volume. That's this number here, represented by purple. It's the expiratory volume. And then as you breathe out as much as you can breathe out, you breathe out this much, it's expiratory reserve volume. The residual volume is the amount of air in the lungs after the most strenuous expiration. Here's the residual volume on the chart here, represented by this teal colored line. It's important to have some air left over in the lungs after you expire, and not have all the air completely gone from the lungs. So that helps keep the lungs open and prevents the collapse of the lungs. The respiratory capacities. These are the amount of air that can be either inspired or expired. So the inspiratory capacity is the total amount of air that can be inspired after a normal tidal volume expiration. Okay, so you breathe in and you breathe out normally. How much air then can you breathe in? If I ask you to breathe in as deep a breath as you can, that's the inspiratory capacity represented here. The amount of air that can be inspired after a normal tidal volume expiration. The functional residual capacity is the amount of air remaining in the lungs after a normal tidal volume. Normal tidal volume, you've expired and there's still air left over in the lungs, that's the functional residual capacity. The vital capacity is the maximal inhalation after maximal exhalation. That's going from the deepest breath in to the deepest breath out. And that's represented here by vital capacity here, from the top down to the deepest breath in. And the total lung capacity is the total volume of air in the lungs. That's represented by this line. There's anatomical dead space in the lungs. This is due to the fact that after you expire all the air, there's still air left over in the lungs and in the alveoli that's used to maintain the expansion of the lungs. Without this dead space air, the lungs would collapse. So the total dead space is the sum of the anatomical and alveolar dead space. It's the sum of non-useful lung volumes. And anatomical dead space is basically the air in the passageway in the bronchi, bronch tubes, but it's not used for exchange of oxygen and carbon dioxide, but it's air remaining in the passageway. It's called anatomical dead space. Minute ventilation is the amount of gas flow into or out of the respiratory tract in 1 minute. Normally at rest you inspire about 6 liters of air per minute. With exercises this will be as high as 200 liters per minute. Now gas exchanges between the lungs and the tissues in 2 types of respiration. External respiration is diffusion of gases in the lungs. Internal respiration is diffusion of gases at the body tissues. Both involve the physical properties of gas and the composition of alveolar gas. So it makes a cycle between gases being exchanged in the lungs. The gases enter the capillaries and enter the bloodstream. It's pumped out to the tissues where during the tissues the gases are exchanged. Oxygen is used up by the tissues and carbon dioxide is put back in the capillaries, and which then enters the venous bloodstream, pumped to the heart and back to the lungs to repeat the process over again. Here's the property of gases. When you put the gas in a container, the presence of a gas in a closed container is going to result in a certain pressure. There's like in this case here, you have a container full of oxygen. There's oxygen molecules inside this container. These oxygen molecules exert a pressure on the walls of this container. If you have a mixture of gases, like in the air, like the air we breathe is a mixture of oxygen and nitrogen, there's going to be pressure exerted by the oxygen molecules, pressure exerted by the nitrogen molecules. The total pressure exerted on the sides of this wall is due to the sum of the pressures of each gas. So if you take the pressure exerted by oxygen and add it to the pressure exerted by nitrogen, when they combine, you have the pressure exerted by both oxygen and nitrogen. And that pressure is proportional to the percentage of gas in the mixture. Let me show you some examples of that. At atmospheric pressure, it's measured at 760 millimeters of mercury at sea level. Nitrogen makes up about 79% of the air, and oxygen makes up about 21% of the air. So the partial pressure of nitrogen, again, nitrogen is 79% of the air. Atmospheric pressure is 760 milligrams of mercury. So just multiply that together. 79% times 760 is 600 millimeters of mercury. That's the partial pressure of nitrogen at sea level. Partial pressure of oxygen is 21% times 760, giving a value of 160 millimeters of mercury. That's the atmosphere. That's the partial pressure of oxygen at sea level. The same ratios hold true even at altitude. At 10,000 feet above sea level, the atmospheric pressure is going to be lower, less atmospheric pressure, and it's 523 millimeters of mercury. How much of that is due to nitrogen, how much is due to oxygen, can be found just by multiplying the percentages times the atmospheric pressure at that level. So the percentage of partial pressure of nitrogen is 79%, multiply times 523 gives you 413 millimeters of mercury. That's the partial pressure of nitrogen at 10,000 feet above sea level. Partial pressure of oxygen you get by multiplying 21% times 523 to give a partial pressure of oxygen of 110 millimeters of mercury. So the partial pressure is dependent, or is proportional to the percentage of the gas in the mixture. The more gas in the mixture, higher percentage of gas in the mixture, the higher partial pressure of that gas. Now, when gas mixes with a liquid, the concentration of the gas that dissolves in the liquid depends on the partial pressure of that gas at the surface of the liquid. Now, that's a fancy way of saying this. If you have a space where you have gas, there's air, and some water or fluid. So you have the certain pressure in this container. This is pressure just could be atmospheric pressure, or pressure that could be due to compression of the airspace. Say you have the air molecules at a low pressure system, and then you push down on the top and you increase the pressure. This is going to force more of the air, force more of the gas molecules to dissolve in the water or in the liquid. Let's apply this to what happens in the body in real life. Let's take the example of when blood comes to the pulmonary circulation. Within the alveoli, remember the alveoli are coming in contact with the capillaries and gases are exchanged. In the alveoli, this is in the airspace of the alveoli, the partial pressure of oxygen is 104 millimeters of mercury. Partial pressure of carbon dioxide is 40 millimeters of mercury. The blood coming into tissue has a partial pressure of oxygen of 40 milligrams of mercury. Partial pressure of carbon dioxide is 45 millimeters of mercury. So when this alveolar gas with a partial pressure of oxygen of 104 millimeters of mercury is able to be in contact with the venous blood with the 40 millimeters of mercury, the partial pressure of oxygen in the alveoli is going to drive oxygen from the alveoli into the blood. Of course, it's higher partial pressure of oxygen in the alveoli than in the blood, so it's going to drive the oxygen into the liquid. It reaches equilibrium in about 1/4 of a second, which is about a third of the time it takes the red blood cell to travel through the pulmonary capillary. The fact that it's so quick to reach equilibrium is helpful, because then if the blood is pumped faster through there, through the pulmonary capillaries, it still would have enough time to get adequate oxygenation. If you measure the partial pressure of oxygen in the blood of a pulmonary capillary at rest, this is the time, this is the partial pressure of oxygen. And blood enters the capillary at time 0. It's going to be deoxygenated blood with a partial pressure of 40. It enters the capillary here, and then within 1/4 of a second, the partial pressure of oxygen is already up to 104 millimeters of mercury. It kind of travels very fast from 40 to 100. And it remains at this level throughout the time that the blood is in the pulmonary capillary. This is the time the blood is entering the pulmonary capillary until it's pumped out of the pulmonary capillary on its way back to the heart. So So what you see is it doesn't take long for the oxygen in the blood to go from 40 to 104 millimeters of mercury. So it very rapidly saturates itself with oxygen during the time that the blood is in the pulmonary capillary. Now let's look at an example of the tissue circulation. This is the blood leaving the lungs. You're going to have 100%, or we're going to have 100 millimeters of mercury. This is partial pressure of oxygen. And in the tissues, the partial pressure of oxygen may be less than 40 millimeters of mercury. So you can see this is going to drive oxygen from the blood into the tissues, because there's higher pressure of oxygen in the blood than in the tissues, so it's going to push the oxygen from the blood into the tissues. The opposite is true from the carbon dioxide. It's going to go from the tissues into the blood. This just kind of describes the same thing. The pressure gradient for oxygen in tissues. Arterial partial pressure of oxygen is 100 millimeters of mercury. The partial pressure of oxygen in tissues is less than 40. That's going to drive oxygen from the arteries into the tissues. Pressure gradient for carbon dioxide is arterial carbon dioxide pressure is 40 millimeters of mercury. In the tissues, the partial pressure of carbon dioxide is 45 millimeters of mercury. This is going to drive the carbon dioxide from the tissues into the arteries. 45 is higher than 40, so it's going to drive carbon dioxide from the tissues into the arteries. We look at ventilation and perfusion coupling. Perfusion is the amount of blood flow reaching the alveoli. Ventilation is the amount of gas reaching the alveoli. Those are not the same thing. One is the amount of blood flowing to the alveoli, one is the amount of air flowing and reaching the alveoli. Ventilation and perfusion must be coupled for efficient gas exchange. You look at the perfusion. The perfusion is altered by the partial pressure of oxygen. Partial pressure of oxygen controls perfusion by changing the diameters of the arterioles. If you have an alveolar O2 that's very high, the arterioles dilate. The fact that they dilate is going to increase the blood flow in that area, because you want blood flowing where there's oxygen for the blood to pick up. If the alveolar oxygen is low, arterioles constrict to minimize the blood flow to that area, because it's low oxygen anyway, so you don't really want to direct your blood to the place where there's no oxygen. So you want to, this ensures that the blood is being sent to the alveoli that has high oxygen. This ensures the most efficient transfer of oxygen from the alveoli to the blood. Ventilation is controlled by the partial pressure of carbon dioxide, and it does that by changing the diameters of the bronchioles. Again, in this situation, in perfusion, we're changing the diameter of the capillaries. In ventilation, we're changing the diameter of the bronchioles, which is the respiratory tree. If the alveolar carbon dioxide is high, bronchioles dilate. They dilate so that carbon dioxide can easily flow out of the alveoli into the third, tertiary, and secondary, and primary bronchi, and out the trachea. If the alveolar carbon dioxide is low, bronchioles constrict, which minimizes the airflow out of the alveoli. This allows elimination of carbon dioxide more rapidly. So these parameters are constantly being monitored by the body, and adjustments are being made to account for alveoli that are functioning more than others, or less functioning than others, or maybe alveoli that might be clogged with mucus. Then that would have a effects on the blood supply to that alveoli. So this is something that's constantly being controlled by the body's homeostasis process. Seen another way, ventilation perfusion coupling. If more oxygen is sensed by the alveoli, the arterioles dilate to increase perfusion. If less oxygen is sensed, arterioles constrict to reduce perfusion. The result is a balance between ventilated areas and in the blood supply in these areas. So you want to maximize the ventilation perfusion. Hypoxia is an inadequate delivery of oxygen to the tissues, and there's several things that can cause hypoxia. There's anemic hypoxia. That's just basically due to having too few red blood cells. Too few red blood cells mean you have little capacity to transport hemoglobin and therefore oxygen. Ischemic hypoxia is if you have impaired blood circulation, so the blood can't flow to the lungs, for example. That would give you an ischemic hypoxia. Histotoxic hypoxia is when the cells are unable to use oxygen. This is in situations where there's a metabolic poison like gas, cyanide gas. The gas is there and it interferes with the transfer of oxygen. There's hypoxemic hypoxia. This is just due to abnormal ventilation, pulmonary disease, and carbon monoxide poisoning. Carbon monoxide has a greater affinity for hemoglobin than oxygen does, so carbon monoxide ties up the hemoglobin, which does not leave any room left over for the hemoglobin to pick up oxygen. So therefore, the tissues don't get oxygen, so they get hypoxic. In the body, carbon dioxide is transported in three forms. About 10% of it is dissolved in the gas in the plasma. About 20% of carbon dioxide is actually bound to the globulin molecule, hemoglobin. And 70%, the majority of carbon dioxide in the body is transported as bicarbonate ions in the plasma. You see here, carbon dioxide is CO2. Bicarbonate, it adds an oxygen and a hydrogen to the carbon dioxide and to form bicarbonate. Carbon dioxide combines with water to form carbonic acid, H2CO3. That's represented here. Carbon dioxide and water combine to form carbonic acid. And so the carbonic acid then can quickly go to hydrogen ions and bicarbonate ions. Just like sodium chloride can break into sodium ions and chloride ions, as carbonic acid breaks into hydrogen ions and bicarbonate ions. Here's our same process here. If you have a situation where the hydrogen ions goes up, the pH is lowered. Just by definition, the pH is lower if the hydrogen ions concentration goes up. If hydrogen ion concentration goes down, the pH is considered to be raised. So the pH is inversely proportional to the amount of hydrogen ions. Now, if you adjust the respiratory rate, if you have slow, shallow breathing, hypoventilation, that's going to increase the carbon dioxide in the body. So the carbon dioxide, think of in this equation, the carbon dioxide is going to go up, and that's going to cause, if there's more carbon dioxide on the left-hand side of the equation, there's going to be more hydrogen on the right-hand side of the equation. So if you have shallow breathing and hypoventilating, it's going to increase the carbon dioxide in the blood, and therefore increase the hydrogen ion concentration. But since it's increasing hydrogen ion concentration, is actually going to drop the pH. That's going to make it more acidic. If you have hyperventilation, where you're breathing rapidly and deeply, It's going to decrease the carbon dioxide in the blood. So the carbon dioxide goes down, the amount of hydrogen goes down. That is going to cause a rise in pH, which is going to drive the blood towards basic, from acidic to basic. The respiration is controlled in the medulla oblongata by the autonomic nervous system. There's a ventral respiratory group located in the medulla oblongata. Here, the nerves stimulate the diaphragm and intercostal muscles via the phrenic nerve and intercostal nerves. Expiratory neurons inhibit the inspiratory neurons. This produces a rate of about 12 to 16 breaths per minute. There's also a respiratory group in the pontine respiratory group. Fine-tunes breathing rhythms for activities like speaking, sleep, and exercise. Here's a diagram showing the pontine respiratory centers in the pons and the ventral respiratory centers in the medulla oblongata, and how it sends fibers to the inspiratory muscles of the diaphragm and the intercostal muscles. If you hyperventilate, you're increasing the rate of breathing, and it exceeds the body's need for removal of carbon dioxide. Decreased blood levels of carbon dioxide is called hypocapnia. And this is what happens during hyperventilation. And hypercapnia causes cerebral vasoconstriction, cerebral ischemia, dizziness, and fainting. That's why you get dizzy when you hyperventilate. Apnea is a cessation of breathing, stopping breathing altogether, and that could be due to abnormally low carbon dioxide partial pressure. The most powerful respiratory stimulant is the rising level of carbon dioxide. So that rising level of carbon dioxide triggers the respiration reflex. Respiration reflex is also triggered by a decline in the partial pressure of oxygen. If it falls below 60 millimeters of mercury, it becomes a major stimulus for respiration. So the arterial partial pressure of oxygen and arterial partial pressure of carbon dioxide are being monitored continuously, and your breathing is adjusted based on these values. There's hypothalamic control of breathing through the limbic system. That example of this would be if you're angry or having pain, you might hold your breath or breathe more shallowly, or when you have a rise in body temperature, you increase your respiratory rate. It's all due to the hypothalamus controlling respiration. And then cortical controls is voluntary control of breathing. An example of this is voluntarily holding your breath. If you hold your breath voluntarily, your carbon dioxide will build up in your bloodstream. And remember, the carbon dioxide is the principal trigger for respiratory breathing. So as the carbon dioxide gets high enough, you're invariably gonna breathe, whether you want to or not. That's why you can't die. You can't hold your breath until you die. You can't voluntarily hold your breath until you die, because the carbon dioxide will go up so much that it will force you to take a breath. This is a diagram. This diagram shows the different neural respiratory centers. There's higher brain centers from cerebral cortex affects breathing. There's the hypothalamus can affect breathing. Breathing is and these has peripheral chemoreceptors that detect oxygen, carbon dioxide, and hydrogen in the pons and in the medulla. So all these factors contribute to the neural control of breathing.